carrying on with continuous distributions. Yesterday we talked about how to find the median and the mode, but I guess the two most important pieces that we talk about as expected value and variance. So let's see how we do that. So x is our random variable, but it's continuous now. The expected value will become, so now we're using integration, as very similar to the discrete. It's still x times function x, but now we're finding the integral from minus infinity to infinity. That'll give us the expected value. Remember, of course, expected value is equivalent to the mean of the data, or the arithmetic mean to be more precise. So here's this model. It's going to model the quarterly salary, measured in thousands of dollars, paid to salespeople in a large company. Now here it is. We're going to look at the median and the mean, describe the distribution of the salaries. So let's do the median first. So the starting point, was it 16, was it? Yes. Starting point is 16. We said for x is greater than or equal to 16. The starting point is 16. We want to go up to m. It's got to equal a half because we want a half of the data. Add 1 to the power over the power. Substitute in. We get 21.112, but of course that's in thousands of dollars. So we know the median quarterly salary is $21,112. Let's now go find the mean. So it's going to be x times the probability of x. So x times x to the minus 7 on 2. Integral to infinity. As much as I hate writing infinity as one of the limits, because theoretically can you substitute infinity, it's probably more correct to go limit as x approaches infinity, or n, whatever pronumeral you put there. But it is kind of acceptable to do it like this. So yeah, as I say, we can't really sub infinity into that. What we're really doing is finding the limit as x approaches infinity of x to the minus 3 on 2. And so if you think of that curve, that would approach 0. So we know we can substitute in 0 for that. So in other words, the answer would be when we substitute 16 in, and when we substitute in 16 we get negative 1 on 64. Well no, when we substitute 16 in we get 1 on 64, but we're going minus that because it's the lower limit. We end up with 26.667, so 26,667. Describe the distribution. Well, if the median is on the left-hand side of the mean, that means more than 50% of the data is to the left of the mean. So we have positively skewed the data. So it's all pushed to the left-hand side. Variance then, how do we work that out? It's probably no surprise then if the expected value looked basically the same, but it's now an integral, the same happens with variance. Reminder, variance is the expected value of x squared minus the expected value of x, or the average, squared. That doesn't change. What changes is how we find the expected value of x squared. So as I say, it's pretty much the same, x squared times the function, but now we're integrating from minus infinity to infinity. Let's find the standard deviation of our salaries then. But in order to find standard deviation, we have to find the variance first. And remember, standard deviation is the square root. So our variance, we'll do that integral, but then we'll subtract the average that we just found. I've written it as a fraction there as 80 over 3 squared. So there's our integral, x to the minus 3 on 2. Again, as we approach infinity, that would go to 0. We end up with 568.889. But remember, that's the variance, not the deviation. So to find the deviation with square root, it's still quite a large spread when you think about it. 23.851 is a very large spread. What happens when you talk about spreads and you look at them? The data will get more clustered around the mean as the standard deviation gets smaller and smaller. So as that deviation gets smaller, you'll see the data pull in to the mean. That is the graph of our situation. Now you can see 23.851, as I said, very large deviation. And you can certainly see the data here is not clustered around the mean. It's a long way from it. There's our median. But if you think about what we're actually measuring here, yeah, it's probably a pretty accurate graph. We're measuring the salaries in a large company. Well, think about it. Half of the people are getting salaries down this end, way down here. It's only the very few that are getting the real large salaries. Maybe a CEO or someone like that. But that is what tends to happen in large companies. The bulk of the people are getting the lower salaries and the very few are getting the high salaries. And there's our average there. That's how it is.